So in previous videos, we graphed sine and cosine, and we found characteristics of both of those functions. We talked about the period, the amplitude, the starting point, or horizontal shift, and increments. And you may hear some books using the word critical values instead of saying increments. But basically, that's what they are. And we're going to talk about why they're critical values in this video. But today in this video, we're going to talk about graphing secant, cosecant, tangent, and cotangent. And the graph, I'm going to cheat a little bit by graphing it in the graphing calculator first. And if you're going to graph in your graphing calculator, if you don't have a cosecant button, you'll probably graph 1 divided by sine of x. Because that's what it is, it's reciprocal of sine. So when you graph that, you see what cosecant looks like. And it's interesting because what you have is all these parabolas here. So you got a parabola going upward, parabola going downward, and you see they start repeat over and over and over, a bunch of those parabolas. Well, if you know why there are parabolas there, you have to understand that this graph comes from the sine function. And these parabolas occur because here we have asymptotes, right here where this line approaches, this curve approaches this line. On the left and right side, we have vertical asymptotes there. And we got lots of vertical asymptotes. We got an infinite amount of vertical asymptotes in the cosecant curve. So for that reason, the cosecant curve does not have a domain of all real numbers. It's something else. We'll talk about what that is in a minute as well. But in order to understand why these vertical asymptotes actually occur and why we have these local mins and local maxes here, it might be best to graph the sine curve simultaneously. So we actually graph the sine curve. You see this, which is nice because now you kind of see, well, this kind of lets you know why we have a local maximum there. Where sine has a local maximum, the cosecant curve has a local minimum. And also where sine has a local minimum, the cosecant curve has a local maximum. And even more important, everywhere the sine crosses the axis of the equation for the axis, or in this case, x-axis, everywhere it crosses 0, the curve has an asymptote. So right here, the sine curve actually crosses at 0. So the sine value, value of sine there is 0. So we have a vertical asymptote right there. And that's one way we can find all those vertical asymptotes. So basically when graphing the secant curve or the cosecant curve, I'm generally going to tell you to graph the sine curve first. And after you graph the sine curve, graph vertical asymptotes everywhere there should be a vertical asymptote, and then graph the curve actually bound in between those asymptotes and where you have a minimum where the sine curve actually has a maximum. Most of the characteristics deal with sine and cosecant are pretty much the same. For example, the period of sine and cosecant are the same. The amplitude isn't, because you really don't have amplitude with secant and cosecant. Amplitude tells you how far you go up from that equation of the axis or the middle line there, and you never stop going up, so you can't really have an amplitude. So we'll say our amplitude is non-existent or undefined, or you just didn't have a number for it, not equal to anything. And the other thing would be the increments, or in this case, I might want to use the words critical values, which is the same thing as the increments. So actually find that, you go ahead and find the critical values for sine. So we think about the period is and that sort of stuff. But I'm going to go straight to this. I already know what they are. For one, I'm going to change my window. So I'm going to make my x minimum 2 pi, or in this case, because it's going to be negative 6.14. And I'm going to make my x maximum 2 pi. So it's going to be a positive 6.14. And x scale will be pi over 2, will be 90 degrees, or in this case, because we're in radians, 1.57. And the y min, I'm just making negative 3. Y max, positive 3. Y, just because it gives us a nice picture. You can choose other numbers. But if you actually graph that, you see this. And every one of these are critical values because special things happen then. At this critical value, at 0, we want to have an asymptote. The next critical value, we have a minimum for the cosecant curve. The next critical value, we have an intercept, or where it crosses the middle there of the line, the equation for the axis. The next critical value represents a minimum for the sine curve, or a maximum for the cosecant curve. The last critical value would be here, where it actually has another intercept, and it would be the end of one period. So all those increments represent critical points of the cosecant curve. We can actually find them. Again, you're going to find them just like you find them with a sine curve, and then graph it later. We're not actually start graphing these by hand. That's enough of this. So looking at a new function, y equals 3 cosecant 2x subtract power of 2. I'll first graph y equals the sine of all that. Y equals 3 sine of 2x subtract power of 2. And I'll find all the characteristics to it and all that stuff. So the first thing we're going to find is the period of it. So the period should found to be pi, amplitude should found to be 3, horizontal shift should found to be power 4, increments should found to be power 4. So if that's the case, I'm going to start off at my power 4 value, the first value, and my increments, or the new word for it would be critical points, will be power 4 from the last. So the next one over will be 2 power 4. The next one over will be 3 power 4. Next one over will be 4 power 4. Next one over will be 5 power 4. And just we can measure, go a little further, 6 power 4. And if I actually graph this, I remember my amplitude had to be 3. So from there, I'm going to go up 3. So this would be 1, 2, 3, down 3. And if I'm going to start with sine curve, it starts low. Next point over is a maximum. Next one over is an intercept. Next one over is a minimum. Next one over is an intercept. Next one over is a maximum again. So here's the curve. So you have to keep in mind this was a sine curve, not the actual curve for the graph. So from there, you'd actually put asymptotes everywhere the graph touched the x-axis, or in this case, touch the axis, the equation of the axis. This is the axis that goes in the middle of that curve. And this is it. So all those places, we have vertical asymptotes. Last thing we actually want to graph is what the actual curve would be. And given all that, the actual curve, one will be here. Another parabola will be there. Another one parabola will be here. And that's actually more than one period of it, because as you see, it was starting to repeat already. So we want to start one period of it, it'll just be between here and there. And that would just be pi. So that length there, this length right here, will be pi. If we started here, subtract backwards, 5 pi over 4, subtract pi over 4, gives you 4 pi over 4, definitely equal to pi. So anyway, that's how you graph that. I mean, I think it's a whole lot easier if you actually graph the sine curve first, opposed to trying to figure out where those maxes and min and all that sort of stuff occurs. So right now, try to graph this one on your own. Pause the video, write down the equation, and actually try to graph this equation in using the previous steps, which would be graph the cosine curve first, and then find all the characteristics, as in period, amplitude, all this sort of stuff. And then graph the equation, and then graph the parabolas that will go with the secant curve. So take a minute, pause the video, try it on your own first. So you should find all these numbers as the increments, and you should find the period to be 6 pi, you should find the amplitude to be 4, you should find the horizontal shift to be 0, and each increment was 3 pi over 2 from the last. So my last one will be 18 pi over 2 minus base as you go to. So we actually graph this because we're looking at the cosine curve, because we're considering this curve, the cosine curve, with all these values here. We actually graph the cosine curve, which we know starts on the axis. So starting at 4, and it's going to go down to -4. And the next point over is an intercept. Next point over is a minimum. And it's an intercept. And then it's a maximum. It's an intercept. Minimum. So we actually graph this. It looks like this. So if that's the case, this is the curve. Now we're going to look for all the places where this graph crosses at 0. Because at those places, we'd have 1 over cosine of 0, which would be undefined. So this would be an intercept. Asymptote. This would be an asymptote. And this would be an asymptote. Last thing, actually, I'm going to graph the curve, and the curve of cosine would appear here. Would be a piece of the curve. Asymptote's there. This parabola would be bound between those two. This parabola would be bound between those two. Last parabola would go in that direction. Just notice there's another piece that goes over there. If you really want to draw it, you could. You don't have to draw this piece off. But that would be it. Those would be all parabolas to it. And I didn't really talk about the domain and range of all this. So domain would be pretty much all real numbers except for these values. All these values here where it's undefined at. So basically I would say my domain is all set of all numbers such that x cannot equal to 3 pi over 2. That being the case, positive negative 3 pi over 2. And the next number would be here, which is 9 pi over 2. Also positive and negative. Next number would be here, which is 15 pi over 2 that actually goes to this point. So the next number would be positive negative 15 pi over 2. Etc. Another way you could have written that domain could be x such that x cannot equal to 3 pi over 2 plus or minus 3 pi over 2 n. And you got a note to it by saying where n is an even number other than 0. So I think 0 is even, not really sure. But that would definitely make it very clear that as long as n is an even number other than 0, you have this right here will represent, this form will represent what the domain cannot be. So those are all the numbers x is not equal to in the domain. Range, it's pretty easy. You look at all the possible y values, and if you actually think about that, we're looking at the lowest y, the highest y value would be infinity, and the lowest y value would be negative infinity. But it wouldn't be from negative infinity to positive infinity, because this graph only exists above this line, only exists below that line. So it's basically all real numbers except those numbers. So we can say our range would go from negative infinity up to here, which would be at negative 4 for y. So negative infinity to negative 4, y is included, the negative 4 is included. And then union picks up again at positive 4 to infinity. So that would be the range to it. The vertical asymptotes could be written as this one or this one. So your vertical asymptotes would be x equals to positive and negative 3 pi over 2, positive negative 6 pi over 2, I'm sorry, 9 pi over 2. Positive negative 15 pi over 2, etc. All right, that's all the time I have for this video. The tan and cotan video, I have to make a separate one. It's going to be connected to this one. So if you look back into the unit, you're going to see a video that says graphing tan and cotan, because I'm reaching my time limit for this. But hopefully you understand how to graph secant and cosecant. If so, good luck.